Hey, Vlad here, devinside.com. Welcome to another video. Today we're going to have a short video, or at least I hope that it's going to end up being short, about stacks, heaps, and the JVM memory model. As always, it's not going to be a full-blown tutorial. It's just the things that I need for you to understand in order to grasp the next video, which is going to be about advanced tail call elimination. So without any further ado, let's get started. As always, we're in the Ubuntu virtual machine and we have Sublime on the left and the regular terminal on the right. I haven't started SBT yet because in the previous video we implemented the red-black trees, and as a reminder we implemented them on the red-black tree branch. So if I do git branch, we will see that I am on the red-black tree branch, and if I switch back to master, which is something that I announced in the previous video that we're going to do, right, then all of these changes should go away. Right, so I click here, the main disappears, this whole red-black Okazaki thing disappeared. Okay, so I'm just going to start SBT over here, and I'm going to create a file. So for now we have a reveal in sidebar. So we have factory, foldable factory sat, and today we're going to implement stacks. So I'm going to create a file called stack, and before we implement stacks, I'm just going to have a hold up, let me copy the package. Right, so I'm just going to have a small main method as a reminder about what tail recursion is actually about. Okay, so we started SBT and let's run our code. Okay, so it's formatting, compiling. Okay, as always we have my hyphens, right, like that. Okay, so let's say that we have an integer called max, and it's just going to be 1,000 for now, right? So we're just going to print it out like this, nothing fancy so far. Okay, so now we're going to have a tiny scope, and in this scope we're going to have an imperative algorithm. We just have a var. We rarely have vars here, but let's have it. So we have a val. So as long as this accumulation is less than max, then we're just going to be adding to the accumulator, and then we're going to print out what has been accumulated, and what should come out is 1,000, right? So we just incremented the accumulator by 1, right? And the tail recursion is a way of writing a recursive function that the compiler will look at and eliminate the tail calls, and basically will convert in something like the while loop. We already talked about this in the video of recursion a long time ago, so this is just a reminder. Okay, so we're going to have a function called loop. It takes this ACC, which is an integer, and produces another one, right? The ACC stands for accumulator, right? So we're going to have pretty much the same algorithm, but instead of while, we're going to use if, right? And instead of just adding stuff, we're going to keep calling ourselves with a +1, and otherwise we're just going to leave the accumulator alone, and that's all. So in the end, we're just going to print out the loop with ACC of 0. So we're starting with a 0, and then we call ourselves was incrementing the accumulator by 1 every time. And we have an annotation in Scala, scala.annotation.tailrec annotation, like this, right? So if that code compiles, it means that the compiler indeed optimized that, not optimized, it indeed eliminated the tail calls. So the compiler was capable to eliminate the tail calls, and thus convert this algorithm into something like this. As I already mentioned in the video about recursion, not every function can be tail call. I'm going to use the word optimized. I know some people don't like it, but it's just like, you know, with the proper English, like, the elimination doesn't fit into my sentences. Okay, so I'm just going to use optimize. So okay, so not every function can be tail call optimized, right? And some functions you can just re-implement in such a way that they become tail recursive, but it is not always possible. So in the next video, we're gonna see what we can do about this. And for now, we're just gonna pretend like we're just going to construct a situation where the compiler is going to say no, right? So the compiler is going to say, hey, I can't optimize this. So I'm just going to copy that, okay? And I'm just going to do +0 over here. So now the compiler is not able to optimize that code, right? But it's still a working code, right? So it still produces 1,000. You know, where adding 0 to an integer doesn't change anything. why is this whole topic even a topic, right? Why is this problematic? Well, it turns out that, you know, if the number is getting too high, then if the tail calls are not eliminating, then the stack will explode. Now, what does it mean? Well, we're running inside of the JVM, and there are a lot of things inside of the JVM, which is a regular application that runs on your operating systems. There are a lot of things that need memory. One of them is the stack, which is something that we're going to implement today. And it simply runs out of memory. So the stack itself runs out of memory. So if we go to, I don't know, 10,000, let's see if it's enough. Okay, no, that's not enough. Let's go to, I don't know, 15,000. Okay, so this is already enough. So you don't see it in SBT, but basically it explodes with a Stack Overflow error. But you know, the errors there, the exceptions are hierarchical. So there's something in SBT that caught this Stack Overflow error and basically wrapped it into a runtime exception, and so on and so on and so on. So we would need to scroll up quite a lot to see the actual Stack Overflow error. Now, as I already said, you know, JVM is a regular application and it has memory, so you might be tempted to increase this memory. So and basically every time an application starts, it asks the operating system to allocate some memory to it, right? And you know, you can every time you start some application, you can pass some parameters to it, and you know, sometimes you can actually give it more memory. So with the JVM, it is actually possible. So today we're going to learn a little bit about passing parameters to the JVM, and we're going to play around with this. And also, a long time ago, I made a video about passing arguments, passing command line flags to applications. So if you want, you know, you might want to check it out. Okay, so the first thing that we're going to do is we're going to leave this alone a little bit, and I'm going to start a new terminal. Where I'm going to just say Java - version. So - version, in fact, it should be just one hyphen, Java - version. So - version is a parameter that you can pass to Java. And if you do Java -x, then you will see a bunch of other parameters. So the ones that we're going to play with today are going to be these three, right? Set initial Java heap space. We're going to talk about the heap in just a minute, and the maximum heap space, and the Java thread stack size. So this is exactly what we need. So there's this parameter XSS that we can pass to the JVM once we start an application. Now the question is, what JVM? Right? So the thing is that that SBT itself is written in Scala. So SBT is a Java application. So what we're going to do now is I'm going to start HTOP, which is something like an application manager, right? So the device manager, not device manager, the task manager. I'm sorry. So if you're in Windows, you can start a task manager. And I'm going to maximize the screen. So over here, if I press F3, then I can actually search for something. And if I search for Java, and then we're going to end up over here. I'm going to scroll down a little bit, right? But it's basically this one. I can press space, then it will be marked. Like usually you mark them just, you know, to kill them or whatever, right? So now I can use the arrow keys left and right to see what was actually in the end. So what it's doing is it's starting Java, passing some parameters, blah, blah, blah. And in the end, it says -jar, which is another parameter. And this parameter itself has another parameter, which is user share SBT bin SBT launch jar. So as you can see, SBT is just another application. So what we can do is we can do this ourselves. So I'm just going to minimize that, right? I'm just going to put it on the left like that. No, not like that. I'm sorry, like that. So HTOP is running on the left. So over here, what I'm going to do is I'm going to start another terminal, right? So this is yet another terminal. I'm going to go to dev, Homegrown Collections. And what I can do, so instead of just starting SBT, I can do Java, right? And I can just, let me go here again. Let me do that. Okay, so I can just let me make it a bit smaller. Okay, so I can just simply do that -jar / user share SBT, and I can use auto completion for that. So bin SBT launch jar, and it should just start SBT as it started before. But in this case, I'm not actually passing any other parameters, right? So this is our homegrown collections. We can run tests. We can do whatever we want. It's exactly the same SBT instance as over there. So now I'm going to kill it again, and I'm going to do the same thing as we just did, but I can actually keep passing more parameters. So I can also do -xms for G, for example, right? So an XMS stands for you know, the initial size of the heap that we're going to talk about in a few minutes, right? So if I start it over here like this, it's going to start SBT. So in HTOP over here, if I look for Java again, they're actually sorted by name. So this is exactly what I just did. I started Java was my parameters, right? So what is it going to say? It says, oh no, I'm sorry. This is the one that I'm sorry that they're overlapping, right? So we have HTOP on the left, we have the original SBT on the right, and now we're having this one that is sort of, you know, floating in the middle as well. They're all black and they're a bit transparent. I'm sorry for that. Okay, so the next thing that I'm going to do is, in fact, maybe let's not make it transparent. If I go to profile preferences, maybe I can just say colors, use transparent background. Okay, so maybe now it's a little bit better, right? So it's just black now. Okay, so it turns out that you also can pass parameters to SBT directly, right? So SBT itself has its own parameters, but if you want to ask SBT to pass those parameters to the JVM, you have to prefix them with -j. So I can do -j, and then I can do this, for example, right? -j, paste that over here, right? It should do exactly the same thing as before. Initially it's set to large. Okay, so this is what happens like when you sort of run out of memory. Let's do like 1 gig. All right, so in HTOP, we should see exactly that, right? So it instantiated Java with 1024 megabytes over here. And it also set XMX for me. Is it this one? Yeah, so the thing is that now because we used SBT directly and not the, not the whole Java command, so it passed like all its own parameters plus the one that we specified. So another interesting flag is this one. So instead of passing only that, we can also pass -xx plus and print command line flags, right? So this one is going to start SPT, right? And it's going to start the JVM, and it will pass that if I hadn't ruined it, right? Because this is for the JVM, right? So I have to do -j. I forgot to do the -j. No. Okay, I also forgot to make the L capital. There we go. All right, so now when it starts SBT, starting SBT again, it's just starting the Java application. It passed this parameter, and this parameter made sure that everything is, that all the other flags are printed out. And this comes back to that thing that I mentioned in the previous video about minimizing the feedback loop. So every time you're playing with something like this, you're passing parameters to something, or you're turning like things on and off. Make sure that you have something to actually see if what you passed over, if you passed in, was actually applied or not. Okay, so by the way, I haven't mentioned it yet, but there are like millions, not millions, but like dozens of ways to pass parameters to applications. So the most convenient one is the one that we're going to use. Actually, let me close like all of that. Okay, so I'm going to close this one, and I'm going to close HTOP by pressing F10. I'm going to close this entire terminal. Okay, so now we're back to like the regular Sublime and the regular terminal with SBT inside of it. And I'm going to make it transparent again a little bit. All right. So what you can do is in the root of your project, right? So over here, we're going to create a new file, and we're going to call it .SBTOps. For options .SBTOps, and basically what we can do is like the same things as we used before. We can pass them over here. All right, so the first one that we're going to do is we're going to pass the -j -xx print command line flags, and with the hash symbol you can write comments. Okay, so also, for example, you can comment this out, like this, then it will not be applied. Okay, now because hashes are used for comments, and I'm just gonna use the name of the command as a comment, we can also set the syntax to bash, right? So the syntax for bash is very similar. So this is not bash syntax, but bash syntax is similar. So I can ask Sublime by pressing Ctrl+Shift+P and just typing bash. I can ask it to set the syntax to the born again shell, to bash, and it's going to look a little bit better. So if you don't want to do it with a keyboard, you can also just click here and then select it over here, and you can also do open all with current extension, and here born again shell. So all the .SPTOPS files will then be opened as with the bash syntax. So I'm just going to leave it like this. So the next one that we're going to do is actually the one that we care about. This is what we originally wanted. We wanted to increase the stack size, right? So the command was XSS, and you're just passing the number. So there's no hyphen, no plus, no colon. You just pass the number over here, right? So let's try to pass 2048 mags, and let's see what's going to happen, right? So over here, I can just kill our SPT. I can start it over again over here. Loading. Okay, it doesn't seem like it worked. All right, so I figured it out. So the problem was that it was called SBTOps without the T, so it has to be OPTS. SBTOPTS. All right, so let's go back to what we tried to do in the beginning. Okay, so let me kill it. I'm gonna start SBT, and now it's gonna say out of memory. Oh, come on, why? Unable to create, hold up. Unable to create new native thread. What? Why? What's wrong? Seems like I have a bunch of memory. Let's just try again. Let's just try again. Oh look, the thread stack size is kind of huge. I don't understand why I tried to do so much. Let's do 47. It's kind of weird. What I wanted to show you originally is actually, okay, now it's working. So what I wanted to show you originally is that if you pass it, if you give it like too much, like when I was preparing this video, it was actually doing basically ignoring it and putting a 0 there, right? So now it worked. So if we take this number, for example, right, and if we just open the calculator in Windows, so if I paste that in and if we divide that by 1024, then we get exactly 2047. So let's try something bigger, because like as I said, like when I was trying, if I was trying to pass like 4 gigs to it, it would start, but it would just, yeah, exactly. So it would start, but as a thread stack size, it would use a 0. So I figured that the maximum is 2047, right? So in any case, let's say that it's 2047. Let's say that this is the maximum. Let's say how much we can get out of it. So let's try to run our application again, and let's see how far we can get. So can we do, for example, int dot max value? This would be the biggest one. So it takes a while, right? But it should eventually. So this is my CPU. It should eventually die. Okay, so it died. So let's try to divide it by, I don't know, 16. Let's see, 16. It should still kill it. Yeah, let's try some like, I don't know, 32. Yeah, that should be fine. So so we got like 6 million. Yeah, so almost 7 million. So let's try something like 10 million, 10, 1, 2, 3, 1, 2, 3. All right, so you can do 10 million. You can do 10 million calls. Okay, so but I'm sure if you keep going like this, essentially it's gonna explode. So the point of this is that you should never rely on the size. Also, like if I keep doing this, so if I keep running it, eventually it might still die, because you know you never know exactly how it uses the memory. Okay, maybe it doesn't, but yeah. In any case, the point is that if you want to leave a recursive method inside of your application that is not tail call optimized, again I'm saying optimized, but I actually mean that the tail calls are not eliminated, then you have to have really strong arguments for that. Now, one of the reasons why we went back from the red black tree branch and back to the master branch, because over here our trees are unbalanced, which means they can degrade to a single linked list. And then, you know, if you're adding like 1,000 elements, it means we're adding 1,000 things, 1,000 stack frames to the stack. So what are we going to do about this? Because we obviously can't eliminate the tail calls from the binary traversals, right? Because we have to go down and up and then down and then up. So so it's obviously not a tail recursive algorithm. So if it happens that the algorithm cannot be tail call optimized, then we can do the following. I'm going to explain more in the next video, but basically the idea is to move the computation from the stack to the heap. Now, what does this mean? So the thing is that every time you have something small, like an integer over here, right? So every time you're in some scope, in some stack frame, every time you're creating a primitive data type on the JVM, like an integer or like a character, for example, then it is allocated on the stack, on that stack frame. However, every time you create an environment, like, I don't know, a new dog or a new person or a new bank account, then only the reference to that environment is stored on the stack, because the stack is so tiny, and the actual object is stored on the heap. Now, heap is also a data structure and it has its own properties, but today we don't really care. Today we treat the heap as this big gigantic pile of data. The cool thing about the heap is that it is not limited, right? So it is only limited by the hardware that you have, and you can actually go to SPTOPS and you can specify whatever you want. So you can go over here and you can say -j, right? And you can say -xms, right? And you can give it ideally, I thought that like this is the initial size of the heap, and I thought that you cannot give it more than what you have. So I'm on a Windows machine which has 32 gigs of RAM, and I have inside of it running the Ubuntu virtual machine which I gave 24 gigs, right? So ideally, I thought that I should be able to give it maximum of 24. even a bit less, because you know the Ubuntu virtual machine itself uses something, right? So something like 22 gigs. But in the preparation for my video, for this video, somehow I managed to give it 50 gigs. So we're gonna try this again. Also, I'm gonna have comments here, right? So this one is the thread stack size. And by the way, the initial thread stack size is only one megabyte, right? This is the initial heap size. And the next one is going to be -xmx, right? These are sort of the three that like every Java developer knows. And you can give it anything you want. So this is the maximum one. So I'm going to use 1 terabyte, right? So this is the max heap size. And somehow it managed actually to create this. So let's see. SPT, yeah, it managed to create it. So let's try that. So maximum heap size, let's do that. In fact, let's not do maximum, let's do the initial heap size. Let's take that, copy, calculator, paste that in. Okay, so divided by 1024, we got kilobytes. Divided by 1024, we got megabytes. Divided by 1024, we got gigabytes. And divided by 1024, yeah, we have our 50 gigabytes, right? I thought we were doing the max one, so I wanted to divide it again, so we end up at 1 terabyte, right? So it worked, okay? And if we run it, it still works. So in the next video, we're going to learn how to move this computation from the stack to the heap by creating our own stack. So we're going to implement the initial very small version of the stack right now, and we're going to use it in the next video. All right, so let's implement the stacks, and I'm going to remove this .SPTOPS file because I just don't want to commit it, because we actually don't need any of these parameters. So I'm just going to delete it. All right, but just remember, just create it in the root folder called .SPTOPS with a T as an options, and then put like on every line you put your commands. You can also do it like globally for all your SPT project, but this way the project becomes a bit more self-contained, which is kind of cool. Okay, so we're in the stack file, and again, this is going to be like a super simple version, right? So we're not going to I'm going to comment this out. So we're not going to make it like foldable. We're not going to write any tests or anything like that, right? So it's just going to be super fast, quick and dirty, the essence of the stack. Okay, so we're going to have a sealed abstract class stack, and it's going to look like the very initial versions of our sets, like before we converted them to trees, right? So we're going to import stack, and stack is going to be an object that is over here. And usually our implementations are hidden, but in this case we don't want to hide them, because we want to make the pattern matching available. So we have the non-empty, same as before, right? Has the element. Really, it's literally the same as with the set. So we have the other elements, which is a stack of elements, right? In fact, maybe let me do it like this, because we're just going to make sure that it compiles in the end. So it's just a stack with an element, right? Remember, it's not private. So we have another one, case object, empty, extend stack of nothing, and the same as before, we have the empty, which is a stack of nothing. This is just for better type inference, right? Empty. Okay, so what we're going to do now is we're just going to implement 3 operations. It's mostly like 2 operations. So you can push something on the stack, and you can pop something off the stack, right? So the push is basically an add. So it's going to look, in fact, you know, I'm going to go to our sets, and I'm going to find the add. Where's our add? I'm just going to copy that, right? It has exactly the same signature, right? But it's just called push. So it's called push, and it's not an override, because we're not implementing foldable or anything like that. And obviously it doesn't produce a set, it produces a stack, right? So all it does is exactly the same as in the set. So in the set, like if you're adding the first element that it produces, like if it's empty, it's just that, right? But if for the trees, it has like the left and the right. Over here, we just have the right, right? We just have the other elements, right? So all it does, it produces this non-empty thing. Okay, so let's check from time to time if everything compiles. Go here, compile. There we go, it does. All right, so let's maximize it again. Okay, and the pop element is basically a remove. Pop element is going to be a removal and the retrieval of the first element, right? So it's going to give you an option of the element, and it's going to give you the other elements basically, right? So it will just do this match. And if it's empty, and notice that this time we can totally pattern match on this, because the equality for stacks is not that expensive as for sets, right? So in this case, the element is going to be none, and the other one is still going to be empty. And if it's a non-empty with an element and other elements, then we're just going to give you the element, and we're going to give you the other elements, right? And that is all, right? So you have push and you have pop. Now, we're also going to have some helpers. We're going to have a final lazy val peak and pop, and it's going to be pop element, right? So this is just a destruction, right? So we're just calling this, it gives you a tuple back, and we're deconstructing the tuple over here to peak and pop. So from the outside, it looks like we have 4 methods now. We have push, we have peak, we have pop, and pop element. Okay, so peak just does the pop element and gives you this, and pop does the pop element and gives you that. And we can't, unfortunately, we can't use a def here because this deconstructing is not going to work. So we're just going to make a lazy val out of it. And this is it, like those 26 lines. This is the entire stack. This is all that we need, you know, for the future videos, and all that we need for today. So let's open the main, so we can just open it and remove everything that we had in there, like that, except for the print lines. Okay, so what we can do now is we can just simply create a few stacks. So the first one is going to look a bit weird because I'm going to have the print line like that. So I'm going to create a stack dot non-empty, right? And we're going to have the 1 over here, right? And then we're going to have the stack dot. I'm not sure if we ever did this with the sats. I don't think that we did, because with the sats, the non-empty one was a private one, so we didn't have access to it. So over here, we can sort of manually create the entire stack. We don't want to do that, but we can. So we have stack dot non-empty, and over here it's going to be the 3, and 3 is going to be stack dot empty. Okay, so this is the print line for the stacks. It looks very, very simple if we actually show it. Right, okay, so we have the non-empty 1, 2, 3, right? So this means that the first element that is on the stack was a 3, right? So if you wanted to do the same thing with stack dot empty dot push 3, then dot push 2, then dot push 1, it should be exactly the same thing, right? So this is a stack with a 1, 2, 3. What did I do? Did I run the push? Let me see the push. Oh, empty. No, it's not empty. It should be this. There we go. Okay, so yeah, see, like even for simple things like this, like, you know, tests are really useful. And usually we want to use the small m-e here, like, so we want to call this one. Right, so when we're doing sats, we didn't really care about the order. In this one, we do care about the order, and notice that the complexity of sats, it was a binary tree, it's logarithmic, adding and searching and so on and so on. Over here, adding is always constant because we don't need to check if it already exists. We just prepend it to the top, and popping the element, same thing, right? We just it's already there. It's just one dereferencing, so to say, and that's it. It was really cool. However, if you want to search something in the stack, then it just becomes linear. Okay, so let's have a few more examples. So let's have a few simple ones actually. So let's have a stack.empty. It looks like this, and stack.empty push 1 looks like this, right? So then if we push the 2 before that, right, like that, push the 2, it looks like that, right? So we have 1, 1, 2, 1, 2, 3. So the first element that is going to be popped is going to be the one that is at the front, right? So it's the one that was pushed the last, right? So let's actually do that. So let's have a few more hyphens like this. Okay, so let's just do the same one as over here, right? Plus the call to the method, right? So this is the peak, this is the pop, and this is the pop element, which is both, right? Pop element, there we go, which is both, right? So it's the same as peak and the pop element, right? As we can see over here, just a simple destructuring. All right, so this is all that we actually need to know for the next video, where we're going to implement some advanced eliminations by using the stack. One last thing that I'm going to show you is that the Scala collection library has a list, and lists and stacks are super similar. In fact, they're pretty much the same. So I'm just going to show you how to create lists. So the first one that we can do is we can do something like this, right? Hold on, let me duplicate that. Okay. However, the non-empty case in the list is called const, so it's pronounced const, but it's spelled as a double colon like this. And the empty one, so you can just do list.empty like that. There is a method called list.empty, so you could do that, right? So the toString of the list is, by the way, like this. Okay, but also, you know, the nil case is actually called nil, right? So essentially, this one is called nil, right? And this one is simply called colon, right? And colon is pronounced const. Okay, so the same way as with our stacks. So you can do, for example, print line list.empty, and then there is no push, but there's another method which sort of, unfortunately, I mean, it's done on purpose, but it confuses a lot of beginners like hell, is that there's the method called like this class as well, right? So there's the method called const, right? And it's basically something like a push. So if we do the 3, and then we do the 2, and then we do the 1, like this. Okay, so this is how it looks like. Same thing, list 1 to 3. Now the reason why it's done that is because of the infix notation. So here's the thing. This code, this one, in fact, I'm not going to use the print line. I'm just going to do this. In fact, why not? So just as a showcase. So this is the same code as without the dots. So this is the infix notation. Like that, right? And was the I'm sorry, like that. And was the infix notation? The infix notation is left associative, which means that the parentheses are being drawn from left to right. So first these, and then them, and then the last ones. I mean, in this case, the last ones are sort of unnecessary. But basically, first this is happening, then this is happening, and so on and so on and so on. However, there is a lexicographical rule that if the method is ending with a colon, then it becomes right associative, right? So if you wanted to do the same thing for the list, right, you might be tempted to do something like that. So instead of stack, we're going to say list, and instead of push, you might say colon, but that's not going to work. So it's going to tell you that colon is not a member of int. So it thinks that, for example, over here, that you're not calling colon on the list that is over here. It thinks that you're calling colon on the integer, right? So this is happening so that you can write code like this. Okay, so this is essentially exactly the same code. So you're calling const on nil, and so the 3 gets prepended, and then you're calling const on a list with a 3, and then the 2 gets prepended, and then you're calling const over here. This const is being called on the list of a 2 and 3, and then the 1 is prepended. We can actually try to do something like that with our method. So we can just copy push, right, and we can call it. Unfortunately, you can only call it, you can only use some weird like operator stuff like that, for example, and only then you can use a colon, right? So if I do this, this is going to compile. It should compile, right? So this will work the same way. Unfortunately, you can't use like words here. You can only use like operator stuff if you want to end them with a colon. But what you can do is you can do something like this. You can do on top of, and you can use the backticks. Right. Unfortunately, you will have to keep using the backticks when you call this method. Right. So on top of is the same as push. So now, similar to this, you can say instead of colon, you can say on top of with a colon. Right. And we have here stack.empty. Right. So this allows you to create like these DSLs where you can say, okay, the 1 is on top of a 2 and on top of a 3 and on top of an empty stack. The last thing that I'm going to show you is the infix notation for the classes like const when you pattern match. So when you pattern match on a list, so let's say you have a list of 1 to 3, and when you match on it, now obviously you can use the constructor pattern about like this. You can say it's a 1 followed by a list of 2 and 3. Okay, like that. 1 followed by a list of 2 and 3. I don't know, print line, yes, and otherwise print line no. Now, if the class has, you know, two parameters, and it does, so this cons, it looks exactly the same as our non-empty, right? So it has an element and it has other elements. So what you can do is you can use the infix notation. So you can do 1 and then colon, so cons list 2, right? So this is exactly the same code, right? So is it a 1 followed by a list of 2? And you can keep going like this, right? So you can say, is it a 1 followed by a 2 followed by a 3 followed by a nil, you know, print line, yes. Okay, so we could do the same thing with our stacks, right? So if we had a stack of 1 to 3, instead of these, we could keep using like non-empty to pattern match on that. And also the last thing that I'm going to show you is this infix notation also works for generics. So if you have a type like map, let's say you have m1, which is a map of int and string, so from int to string, which is a map of 1 to that. Okay, so let's print out m1. What you can also do is you can create m2, right, and then use the infix notation for the type. It's sort of rare, but sometimes like people write DSLs like on purpose to look like this, right? So this is the same, essentially the same thing. And you can do the same thing for the functions. What happened? My max map. It's map. All right. Whoops. Okay. Come on. Okay, so you can do the same thing for the functions. So if you have f1, which is a function from int to string, and by the way, maps are functions, right? So they basically take an integer, return you a string, right? So you can just say m1. And the same thing you can do f2, which is, you know, int function string. This is super rare, but you know, occasionally you might see this, right? And this is sort of where this notion is also coming from, with the arrow, right? So instead of the word function, you can literally use the arrow, right? Like this. Unfortunately, the other notation is not going to work, right? So you can't do f4 and then this and then int string. Like this is not going to work because I think this is like you know, the arrow is like a compiler thing, so this is not it doesn't apply, you know, these rules don't apply. So this is actually not going to compile. I also don't think that you can, maybe I can do parentheses around this. No, like this is just not gonna fly. All right, so this is all that I wanted to show you today. In fact, I'm gonna remove the main, and let's just for fun run our little test. You know, we didn't actually touch the sets, but still, let's run our test. Okay, so let me get out of here. Let me press Control L, git status, git add this file, commit -am. I'm just gonna call it stack. So it's video 12. I'm just gonna call it stack, but you know that it was not. Oh, come on. There we go. That it was not only about stacks, it was also about heaps and passing JVM parameters and so on and so on and so on. All right, so I'm gonna do that, and I'm gonna push it. And by the way, notice that we can do this. Come on, hold on. Okay, so we can do this git log thing, and notice that the video 11 is missing, right? In fact, if maybe we can, if we check out the red black thing, and if we do the log thing, I thought it would show this, you know, this like a tree kind of thing. Doesn't matter. All right, so let's push everything. Actually, let's switch branch back to master. No, I meant checkout master, git push. All right, maybe it actually works like right now with the git log thing. No, still doesn't. Okay. Anyway, so again, this is all that I wanted to show you today. The way stacks work and the way that you can implement stacks, you know, inside of the heaps. And because you know the heap is only limited by your hardware essentially, then you know you can move the tail recursive the recursive methods that where the compiler cannot eliminate the tail call. You can move them to the stack, and at least there you have like so much more memory that this basically doesn't become an issue anymore. It stops being an issue. All right, anyway, I'm talking too much. I recorded 3 videos today, so I hope you liked this video. Subscribe if you want to improve the developer inside you. Most importantly, take care.